Good evening, everyone. Welcome to the first distinguished lecture of the 2025 Space Studies program here in Ansan, Republic of Korea. My name is Anna Cordray. I am the director of the program, and tonight I have the privilege of introducing Dr. Jeffrey Hoffman, former NASA astronaut, astrophysicist, and professor. Over the course of 5 space shuttle missions, he's logged over 50 days in space. Achievements. The first mission to repair the Hubble Space Telescope. His contributions to human spaceflight, exploration, and science are matched by his dedication to education and advancing our understanding of space here on Earth. Today, he continues to inspire the next generation as a professor at MIT and as a leader of space systems research. So please join me in welcoming Dr. Jeffrey Hoffman.
Thank you, Anna. Well, you see Hubble up there. Hubble has been up there since before most of you were born. But, you know, it's a great story. We learned a lot from it. And I've been fortunate to have played a pivotal role in it. And look forward to sharing some of that with you this evening. Let me just restart here. There we go. So first of all, why go to the trouble of putting a telescope in space? I mean, it's a lot less expensive to build a telescope on the ground. But, you know, telescopes on the ground have to look up through that atmosphere, which does a bunch of things. It is always moving around, so it distorts the images of all the things that we look at, and it absorbs a lot of the electromagnetic spectrum. So, of course, we see the visible light that comes through, but ultraviolet light, infrared light doesn't make it through. And so it's been a dream of astronomers since the birth of the space age to be able to look at the heavens with what they imagine would be a large, optically perfect telescope in orbit around the Earth. But not just any kind of a telescope. When you have a telescope on the ground, of course, the critical part of any telescope is the mirror, which, like in Palomar, it's down here. And once you build the mirror for a telescope, it's good for decades, for generations. But the detectors that you put at the focal plane of the telescope constantly improve, sort of like Moore's law. And of course, when you build a telescope on the ground, if anything breaks, you can fix it. But more important, when new detector technology becomes available, you can remove the old detectors and put the new detectors in. We never had the capability of doing that in space. That was the dream of the Hubble telescope, not just to have a large optically perfect telescope in space, but to make it serviceable by astronauts, spacesuited astronauts working out of the space shuttle. And, you know, this is the mirror that ultimately went into the Hubble telescope. Now, I'll have a lot to say about the mirror and what went wrong, but this was the original goal. Was essentially, you look at the wavelength, and when you study optics here at ISU, you'll learn that the actual resolving power depends both on the wavelength and the size of the mirror. And when you're seeing over, here in the ultraviolet portion of the spectrum, we had, you know, better than 1/10 of an arc second of resolution. That is very, very fine for a telescope. So, you know, when you the Hubble telescope used the telescope technology of the mid-20th century, just like the Palomar telescope, the 200-inch. You start with a big chunk of glass and you gradually machine it to just the right shape. Just to say a little bit about the shape of a mirror, up at the top you can see this shaded section. This is the surface of a sphere. And when you're grinding a mirror, that's the easiest shape to make, is a spherical mirror. The problem with a spherical mirror, as you can see, the light rays that hit the outside of the mirror are focused at a slightly different point than the light rays that hit near the center of the mirror. That's called spherical aberration. You can get rid of the spherical aberration by making a parabolic mirror where all the light is focused at a given point, and that's fine when the light is coming straight down. There's other types of aberration for light that is coming in at an angle, and I won't go into the detail. It's called coma. In order to have a telescope mirror that's perfectly free of aberration, you have to make both the primary mirror and the secondary mirror with complex hyperbolic surfaces. This is the basic mirror arrangement, and they're put into the telescope so that the light basically comes in at the top, bounces off the primary mirror, bounces again off the secondary mirror. There's a hole in the middle of the primary mirror, and then you put all the instruments in the back, and each instrument has a little mirror which sticks into the train of light and gets that light into the particular instrument. To build a complex telescope like this that you can put into space and make it serviceable is something that had never been done before. And whenever you start to do something that's totally new and that's going to require a lot of new technology, what inevitably happens is it's over budget, it's behind schedule, and sure enough, there was a lot of complaints about the budget and the schedule of Hubble. This was a typical article, will it ever lift off? Well, yeah, finally in the spring of 1990, with great public fanfare, Hubble was taken up in Space Shuttle Discovery and put into orbit. And I have to say, there was a lot of publicity when this was being done. The public was very enthusiastic because there were all these discussions about all these incredible things that this new telescope was going to tell us about the universe. So incredible expectations waiting for the first images to come back from this telescope. And, you know, we waited and waited. And, you know, when you pick up a new pair of binoculars, the first thing you do is you take the little focusing thing and you go back and forth and you find the sweet spot in the middle where everything is in focus. And that's typically what you do with a telescope, and that's what they were trying to do with Hubble. And, you know, this is not a suspense story. You all know the basic story that, in fact, it couldn't focus properly. This is the best image that they could get of a nearby galaxy, and when you tried to get an image of a star, instead of a point of light, it was spread all over the place. It was a disaster. People who, I mean, none of you in the audience lived through that time. I mean, it's hard to recreate what a disaster it was. I mean, Hubble was a butt of joke with late night comedians. It was denounced in the halls of Congress as a techno-turkey. It was a disaster for the astronomical community. Many astronomers had spent a large part of their life getting ready for Hubble. NASA at the time was trying to convince Congress to give NASA the money that would eventually become the space station. Congress was fed up with NASA. Basically, they said, do something about Hubble, and then we'll talk about the space station. So, what do we do? Well, this was the basic problem. What you see on the left with the X is the amount of the light which should have been focused to within, as you can see, less than 1/10 of an arc second. Instead, this is what Hubble was doing. The light was spread all over the place. So the first thing that you have to do when you're trying to solve a problem is figure, what is the problem? How did this happen? Well, we go back to how the mirror was actually manufactured. As I said, you start out with a big piece of glass. It's flat on top, and then you grind it away until you can get the right complex hyperbolic shape. Now, probably nobody here anymore grinds their own telescopes, but when you make a telescope, the easiest thing to make is a spherical mirror, as I said, and there are certain optical tests, interferometric tests that can be done where you get the right interference pattern, which tells you, yes, you have a proper spherical mirror. Now, as I said, the mirrors on Hubble were not spherical. They were much more complex. So in order to make this sort of measurement, they had to use a secondary telescope, which was put on top of the actual mirror, which effectively made this hyperbolic telescope mirror look like a spherical mirror so that they could do the tests on it. And in order to do that, it had to be put at exactly the right position with respect to the mirror, which was accomplished by what they call a metering rod. So you can see how this is what puts it in the right position. This is a picture of that metering rod, and of course, after the disaster when Hubble couldn't focus properly, they went to the factory at Perkin-Elmer in Connecticut where the mirror was ground, and they got all of this equipment. Now, up on top of this metering rod or measuring rod was what they called a field cap, and then the whole thing was put into a device to put it at just the right position from the mirror. And they interviewed the technician who installed that metering rod. He said, yeah, I had a lot of trouble getting that thing in. I had to use a couple of shims. Oh my God. He never told anybody. I mean, there were a lot of things that happened along the way that should have raised a lot of red flags. But when the people designed this metering rod and that field cap, they allowed for the fact that, possibly it might be installed incorrectly. So we need a way of measuring exactly where it is, and this is how they were going to do it. On top of that field cap, there was a little hole, and you could shine a light down and use that light to measure exactly the position of the metering rod to make sure that it was in exactly the right position. It's possible that some of the light might have actually hit here, in which case it wouldn't be measuring the right position. So to ensure that only the light that went through that hole would be reflective, they put this non-reflective coating on top of the field cap to make sure that the measurement would be done correctly. Well, they've managed to find the field cap. It was in a closet somewhere, and wouldn't you know, a little bit of that non-reflective coating had peeled off. And so, in fact, the measuring rod had been incorrectly installed, but just by, talk about bad luck, this is what the situation was. This is what they thought they were measuring, but in fact, this is what they actually were measuring. It looked like this 1.3 millimeters happened to be exactly the same as the misplacement of the field rod, but it looked like the field rod was in the right, the field cap was in the right position. And that 1.3 millimeters, which is not a lot, but that resulted in the actual shape of the mirror being incorrect because they used that reflective null corrector, that little extra telescope, to tell them that the mirror was in the proper shape, whereas in fact it wasn't. The mirror had been made slightly too flat. In other words, instead of the proper hyperbolic shape, a little too much glass had been taken off the outside of the mirror. How much? About 1.5 microns. The average human hair is 50 microns. So you're talking about 1/50th the diameter of a human hair error in the mirror. But the optics of Hubble was so precise that that made all the difference. So once they had figured that out, then you can start doing simulations of what it would be like. And in fact, when you run the simulation of, let's see what would happen if the mirror had been ground this way by mistake, and sure enough, the computer-generated images look very similar to the actual images that we're getting. So we were basically confident that we knew what the problem was. The mirror was slightly the wrong shape. Now the question, what are we going to do about it? So, what can we do to fix the problem? Well, as I said, the way the telescope works, all the light eventually comes down in what should have been a focused beam, but is actually slightly out of focus. But each of the detecting instruments has a little 45-degree mirror. This is just a schematic, but basically each of the instruments shares a little bit of the light that's coming through with that mirror. And so the solution was, for each instrument, we would have to introduce 2 additional mirrors, each of them about the size of your thumbnail, so that the out-of-focus light was intercepted before it went into the instrument, bounced off a second mirror, which was slightly curved to compensate for the lack of curvature of the primary mirror, and then that properly focused light would be put into the instrument. Now, if an instrument is still being built on the ground, and remember, Hubble was designed so that we could continually take out old instruments and replace them with more up-to-date, more modern, more powerful detectors. And so, for instance, on our mission, one of the things that we did was we took out the first wide field camera and we replaced it with one which was still being built at the Jet Propulsion Lab. And so they were able to put this optical correction into the instrument before we ever took it up, and all we had to do was, I mean, it was not so easy, but we took out the old instrument, put in the new one, and the optical correction was built in. But there were a bunch of other instruments which were not going to, we didn't have any replacements for them. And so how were we going to correct the optics for those instruments? And this was very clever. They took out one of the instruments and replaced it with this big box which had inside it a whole bunch of mirrors sort of folded up like the skeleton of an umbrella. And we would insert this, and then once it was inside the telescope, each of those mirrors would basically pop up into the right position so that they could do the correction. And this is kind of a schematic of how it worked. It was an incredible tour de force on the part of optical engineers, mechanical engineers, astronomers, astronauts. But the good news was it really looked like we had figured out what the problem was, and we knew what we had to do to fix it. And now from our point of view inside the astronaut office, of course, the big question was, who's going to get to do this? Because as you can imagine, this was a primo mission that everybody would love to go up and fix Hubble. Well, this was such a critical mission, NASA decided they would do anything possible to reduce the risk of failure. If you could come up with an idea that would improve the chances of success, even if it was going to cost some money, you could get it done because it was Hubble. And one of the things they decided, by the way, there were numerous other problems with Hubble. The solar panels, every time they went from light to dark, the thermal stress would start them vibrating, so they had to be replaced. There were tape recorders which had failed. There were other electronic instrument boxes. In all, there were about a dozen things that had to be fixed. The optics were most important, the solar arrays were critical, but all these other things. And when they actually went and did the timing of how long it was going to take, they decided that it was going to take 5 spacewalks in order to accomplish all those things. We had never done a mission with 5 spacewalks. This was something that would be completely new for NASA. And because it was so critical from a spacewalking point of view, they decided that only astronauts who had previously done a spacewalk would be eligible to be on the spacewalking crew for Hubble. And here's where luck sort of played a role in my career. This was me on my very first flight. Oh God, I look so young. I love it there. Originally, our mission was just to take 2 satellites up and launch them. And the first one worked just fine. And we launched the second satellite. And this little rod here was supposed to pop up after about 2 minutes. And I remember staring out the window, and I commented to my partner. I said, wasn't that antenna supposed to pop up? This was after about 5 minutes. So I called down to the ground, Houston, we got some sort of a problem here. The satellite doesn't seem to have activated. And sure enough, it was dead in the water. They looked, whenever you have a problem, the first thing you always look for is a single point failure. And of course, we were not planning to do any spacewalks. I had been trained how to use a spacesuit with my colleague, but there was one potential single point failure. There was a little switch on the outside of the satellite, which when it was in the shuttle was depressed. It's kind of a safety. This was in the whole ignition sequence. You don't want the satellite's rocket motor to turn on when it's inside the shuttle. That would be a bad day. So when it's released from the shuttle, the switch opens up, but there's a little micro switch underneath, and that's the one thing that possibly we might have access to, because we didn't have any special tools or anything. So I'll always remember the call coming up from Houston that, Space Shuttle Discovery, Houston, we've been thinking about this problem. We've got some potential solutions, one of which might involve a spacewalk. Spacewalk, we heard. No, they're never going to let us do a spacewalk. NASA had never done an unplanned spacewalk in its entire history. Whenever you were going to do something outside, you spent a lot of time underwater practicing what you were going to do. We were trained to use a spacesuit, but we had never practiced doing this. But sure enough, they said, all right, let's do it. And we had to make some special tools. It was a little bit like that Apollo 13 movie where they said, throw everything you had on the table and figure out something that they can use to flick that little switch. And so we came up with, you'll see a picture of them later, these little things which looked a little bit like fly swatters. So we became known as the SWAT crew. And sure enough, we got ready for our spacewalk, went out. And there you can see the fly swatters. And we went up, and sure enough, we flicked the switch, which it turned out what we did was completely successful. That single point failure was not the actual failure. But knowing that it wasn't a single point failure, another crew went up with full equipment 3 months later, and they actually captured the satellite and hardwired. They actually opened it up, hardwired. It's something we couldn't have done. We didn't have any of the equipment. But in any case, it was a successful spacewalk, and that put me in line to be named as one of the Hubble crew. And so there we were. With the 5 spacewalks, it was considered too much for just 2 people to go out 5 days in a row. And so we actually had 2 teams of spacewalkers. So my partner Story and I went out on days 1, 3, and 5. Tom Akers and Kathy Thornton went out on days 2 and 4. Claude Nicollier, a Swiss astronaut from the European Space Agency, ESA had financed 15% of Hubble, so they had an astronaut on board. He operated the robotic arm, and then Dick Covey was our commander, Ken Bowersox, the co-pilot. And then we went in for a period of intensive training. This is the training for the remote manipulator. We were the first crew to introduce virtual reality, which is now a standard part of training. The VR was pretty basic in those days. The update rate was about a half a second, so you had to move your head really slowly so you didn't get ahead of the actual VR, but it proved to be very useful. But most of the training for a spacewalk you do underwater. And we spent about 400 hours underwater training for this mission, rehearsing everything, because the critical limiting factor for this mission was our EVA time outside doing useful work. And so we really had to work to make sure that we didn't have any wasted effort, any wasted time. We tried to streamline everything we were doing, and we rehearsed these things over and over. You know, are you in just the right position to be able to insert this, and what can we see? I mean, it was incredible training. And because it was Hubble, just as an example, I could be in the water one week and say, you know, I'm trying to get at this bolt with this wrench, and if there were a 20-degree bend in the head of the wrench, I could probably get at it a little bit easier. Under normal circumstances, they would just say, hey, deal with it. Don't give us any trouble. But this was Hubble. So the next week I'd come into the water, and sure enough, there would be a wrench with a 20-degree bend in the top. So it was incredible. Everybody at NASA was working for this one goal. There was no inter-center rivalry. If you could think of anything that would increase the chances of success, you could get it done. Another example, you know, we were moving around fairly massive pieces of equipment, which, although they don't have any weight, they have inertia. When you're in the water, there's a lot of resistance. So, you know, you're pushing around these big objects here, and you have to push pretty hard to get them to move. But up in space, there's no resistance. And if you push as hard in space as you do in the water, things are going to get out of control. So in order to allow us to really get the feeling of what it's like moving things with no gravity, they built us these devices on an air-bearing floor, sort of like an air hockey, where everything is sliding motionless, at least in 2 dimensions. So you can see, you know, this is the mock-up of the instrument that we were going to install. Here is a model of that, the same mass and moments of inertia, and both I and that instrument are on this air-bearing floor, so we have complete freedom of movement, and you can totally get the sense of what it feels like, where you just have to use fingertip motion, very, very gentle, to get these massive things moving around. And of course, we spent a lot of time at the Goddard Space Flight Center, where these instruments were being prepared, the new ones, because this is the big clean room we have there. Of course, the mock-ups we used in the water tank, you don't want to put a real instrument underwater, so it was good to get a look at the actual instruments that we were going to install. After a lot of training, We get in our T-38 jets, fly down to the Kennedy Space Center. I'll never forget the night before launch, there was a total eclipse of the moon. I was walking along the beach and walking, looking at the moon coming back, and then they light up the whole shuttle. They roll back the launch protection, and we all go out to see the so-called night viewing. And then finally the day comes, and yeah, it's quite a ride. Lots of vibration, lots of noise. That loudspeakers doesn't do it justice. I mean, even from 3 miles away, the visitors, they say the ground is shaking, and it's a pretty wild ride inside. But after about 8.5 minutes, we were in orbit, and we didn't waste any time. This was an airlock normally built to hold 2 spacesuits, and we had 4, so it was pretty crowded. This is where we put all of our delicate equipment inside these foam packages to protect them from the vibration of launches. Tools were absolutely critical for this. We had lots of specialized tools, about 200 tools in all, about half of which we were planning to use and half of them in reserve. First thing you do on a spacewalking mission is you get out your suits, and we spend several hours just checking out the suit. Remember, a spacesuit is like a miniature spacecraft. It's got to provide you with oxygen, with pressurization, with thermal control, with radio communication, as well as give you the freedom to move and do useful work. And your life depends on it, so you want to be sure your spacesuit is in good shape before you get in it and actually go out into a vacuum. The back of the spacesuit, we have carbon dioxide scrubbers and batteries. When you're getting ready to do a spacewalk, I get up early in the morning. I have a big breakfast because I know I'm not going to get anything to eat for the next 8 hours or so. We get water inside the spacesuit, but really no food. Hubble was up at about 600 kilometers, which is the highest the shuttle ever went, and we were sort of brushing the inside of the Van Allen radiation belts. So we knew we were going to get about 10 times the average radiation dose of a shuttle mission. Nothing to be worried about, but they had us wear these special radiation monitors in different parts of our body because they wanted to find out, how much dosage you get at different parts when you're out in a spacesuit. Don't usually show pictures of myself in underwear in the public, but this is a special case. It gets pretty cold at night when you're in the dark, and so we wear a layer of long underwear, sort of like when you go skiing, although the atmosphere inside a spacesuit is pure oxygen, so it's all made of Nomex, which is fire retardant. And that little orange thing you see there, we refer to politely as a UCD, which is a NASA speak for a urine collection device. Nowadays people have replaced that. They normally wear diapers, but I was old school. And then, of course, when you're in the sun, it can get pretty hot. And so on top of the thermal underwear, we wear this, what we call a liquid cooling garment, where you have lots of tubing through which you circulate cold water, and you can sort of dial it up to control the temperature to make it as warm or as cool as you need it, depending on how hard you're working. Then you put on the lower part of the spacesuit and then float into the airlock. And that's looking up into the upper part of the spacesuit. The U.S. spacesuits come in 2 parts, the upper and the lower. Getting into the upper part, it's quite a squeeze, but once you're in there, we We then basically put on a helmet. We run the spacesuit at about 3/10 of an atmosphere of pure oxygen. Why at that pressure? Think of a spacesuit as an anthropomorphic balloon. You've all played with little party balloons, you know, the long ones that you blow up, and you know when you try to bend them, they want to snap back. And the spacesuit is just the same. You go to bend your arm, it wants to snap back, and the higher the pressure, the stiffer the suit. And of course, we want to be able to do useful work, so the lower the pressure in the suit, the more flexible it is. So we don't waste any pressure on nitrogen. That's why we just use pure oxygen, and in order to, the minimum you can get to and not get hypoxic is about 3/10 of an atmosphere. So that's what we have inside our suit. But if you go from atmospheric pressure to 3/10 of an atmosphere, anybody who's a scuba diver here knows you'll get the bends. Nitrogen will bubble out of your blood. And so we actually have to purge our suit of all the nitrogen. So we run pure oxygen through the suit for about 20 minutes. And then we start what we call a pre-breathe clock. And so for 40 minutes, we just sort of sit in the suit and breathe pure oxygen. And that gets enough of the nitrogen out of our blood so that we can depress the suit to working pressure without worrying about getting decompression sickness. And at that point, we are ready to go outside, and I have a little video of what we were actually doing. So there I am coming out on the first day of the very first spacewalk, getting ready to, the job on this day was basically to replace the gyroscopes. So we're going up there. One of us is always standing on the end of the robotic arm, and the other person is what we call free floating. We're both attached by a umbilical cord to the shuttle. And you can see I have Story is actually inside the telescope. I would undo the bolts, he would remove the gyroscope, hand me the old one, I'd hand him the new one, he'd put it in place, and then I'd tighten up the bolts. And then being very, very careful, because the one thing we did not want to break anything in the telescope that was not already broken. So getting him out very, very carefully.
Okay, Jeff, and just for my paperwork, can you read me the serial numbers off? Sure will. I'm getting ready to put away 1,000.
What's happening here, I mean, they were so particular. They wanted to be sure that we had not made any mistakes and had taken out one of the old ones and then by mistake put one of the old ones back. So I had to read all the serial numbers. I mean, that's the level of detail that we went to. We then folded up the solar arrays because they were going to be replaced with new improved ones the next day, rolled up sort of like an old-fashioned window shade. The second one, unfortunately, you can see it's not looking very healthy because one of those supporting rods had buckled due to thermal stress, so we actually had to throw it away, and it stayed up there for a while and eventually burned up in the atmosphere. But it was pretty incredible looking at it. We had to fire our maneuvering rockets to move away from it, and there you can see what happens when the exhaust hit it. It was sort of flapping like the wings of a giant prehistoric bird. And then we installed the new ones, which eventually were removed and replaced by even better ones. So this is on the third day, when now we're actually going to remove the old camera and replace it with the new camera with the improved optics built in. This is the moment that the astronomers were all waiting for. You can see we hung the old one over at the side there, and here we're taking out the new one. All of this is speeded up by a factor of 3. We move very slowly when we're moving out there, but it would just be painful to watch it in real time, so we speeded all of this up. We were prepared for all sorts of problems, and we had hammers and hacksaws and whatever it was going to take to get that in, but everything worked beautifully. We had two major problems, which I'll talk about after the video, just to give you a sense of what we had to deal with. But there we're putting the old one away and brought back. It was actually on display in the Smithsonian for a little while.
There we go. One foot to port, one to port.
And then on the fourth day, we are going to put in the second of the corrective optics. Remember, I showed you this is to replace one of the observing instruments, and up here is where all those mirrors are ultimately going to pop out. You can see Kathy's holding on to it. She can't see where she's going, and it's a very tight fit. So Tom is actually inside the telescope to guide it in. And again, we had to be very careful that we don't want to break anything that is not already broken. But it all worked. This is an example of how we use the power tools. They get the job done so much faster, and they take a lot of wear and tear off your wrists. And look at all the tools that are hanging from the tool carrier on Kathy's chest. They're just, and every single one of those tools has to be on a tether. After each spacewalk, we have to clean and disinfect the inside. There's nobody in that spacesuit, by the way. Astronauts are flexible, but not that flexible. And then here's the final day, and this was just one of those incredible moments where we were replacing the magnetometers up on top of the telescope, and Story and I were up there basically in the middle of nowhere. Finally deploying the new solar arrays and getting ready to basically finish up the last of the spacewalking tasks. Remember, this was a spacewalking mission that was so complex that there were many people who thought that there were too many things we were trying to do, that we really wouldn't be able to accomplish anything. But after the fifth and final spacewalk, we had basically done all of the dozen problems and actually fixed one other, which we found along the way. And we were really quite happy and believed that everything had worked so well. And at this point, we weren't quite ready to celebrate because we still had to release the telescope and get it back into orbit. But we knew that basically our spacewalking jobs had been done, and we basically had to get the telescope back into orbit, which was the job of Claude operating the robotic arm. It's very delicate. If you start the telescope tumbling when you release it, you're going to lose the telescope because it doesn't have any active reaction control system or jets. It just has some reaction wheels. But it worked fine, and then finally we move away from the telescope very carefully so that we don't plume it with our exhaust. And here's a few pictures that I took just to show after we had installed the wide field camera. We had to wait for about 5 minutes while the ground checked that all the connections had been made properly. And so that gave me a chance to take a few pictures just to show what it looks like when you're up fixing Hubble. And look over here. By the way, this I don't show this to anybody from the Flat Earth Society because they might get the wrong idea, but we were using very wide-angle lenses which cause a lot of optical illusions. And I'll leave this one up to you. This is the transparent Hubble Space Telescope. You can see the Earth right through it. Think about it for a while. And as hard as we were working, every once in a while, they'd call out, hey, get ready for another space sunset. And you just sort of have to look out there. at least for 5 or 10 seconds, enjoy the view. And looking up at the telescope, I mean, it's 15 meters, 50 feet from bottom to top. It's big, and particularly when you're at the bottom and looking up, I mean, it's a long way to go up there to the top, and that's where we were when we were fixing those magnetometers. And this is an image. That's me with the red stripe there. Just sort of hanging on and watching the world go by. This feeling will be with me for the rest of my life. But it's a long way down and not a place for somebody with vertigo. We did have 2 significant problems, and I'll just talk about them briefly to give you a sense of what we had to deal with. Remember when we were replacing the gyroscopes, they have these 2 big doors, and after we successfully replaced the gyroscopes, then a story went off to do some other work, and I went to close the door. And when I went to, the door has 3 latches, one in the middle, one at the top, one at the bottom. I closed the middle latch, no problem. Go to close the top latch, and the little screw was about 2 centimeters away from making its proper contact. The door was warped. It wouldn't close. I opened up the middle, closed the top, then I couldn't get the bottom closed. We had a real problem. I played with it for maybe 30 minutes, finally figured out it was going to take 2 of us. I was going to have to push on the top with one hand, close the latch with my other hand, and of course I was standing on the arm, so I could react that force. I could push against the door and react the force against the arm. I called Story over to do the bottom part of the door. Of course, he was free-floating. He had nothing on his feet. So he had to use one hand to stabilize himself. He used his second hand to push the door close. And if he had had a third hand, he could have locked it with put the latch together. So we spent a lot of time trying to figure out what to do, and we finally figured out we could make use of a specialized tool. Some people in the ground were worried that we were going to break the telescope, and they didn't want us to do it for a while, and we were going back and forth, and finally, ultimately, it's the job of the flight controller to make these decisions. And I remember when he called up, he said, "Look, guys, we're running out of time. Jeff and Story are in the best position to know what is going on. We just got to trust them to do the right thing." And we went ahead and we got the door closed, and that was the end. The other real problem we had was on the 5th day. We were replacing the controller for the solar panels. Most of the equipment was specially made to be what we call EVA friendly. In other words, big bolts, nothing tiny, but they figured that this piece of equipment was so simple, and they had a backup, that they didn't have to really design it to be replaced by spacewalking astronauts. So they designed it with these tiny little 2mm screws, if any of you remember SCSI connectors in the old days of computers. And so we were out there taking out these tiny little screws, and we had a little trash bag that we would put the screws in, but after a while, you'd open the top of the trash bag to put a screw in, and 2 screws would float out of it. They've since redesigned the trash bag, but that's another story. And then at one point, Story reached for one of the screws and didn't quite get it, and the screw started floating down towards the cargo bay, and you don't want extra pieces of metal down there. It might get in the way of some motor. So I was free-floating that day, and I reached out to try to grab it, but it was about a foot away from my hand. But I was holding on to the arm, and so Claude, who was operating the arm, said, well, just hang on, Jeff, I'll drive the arm and you can get the screw. Well, it turned out that the maximum speed of the arm was the same as the speed of the screw that was moving away. So, I was reaching out and the screw was continually a foot away from me. And here's where training comes in handy, because there's a particular software that operates the robotic arm, and when there's any load on the arm, whether it's a person or a satellite, the speed of the arm is limited. So Ken Bowersox, who was the backup arm operator and knew this software, went over to the computer and basically told the computer, no, there's nobody on the arm, and so the arm sped up and I was able to catch the screw, and that was the great screw chase, and it all turned out happy. So that was basically, we knew that we had succeeded in our mission, but what we didn't know was, of course, would the corrective optics really work? And you can't turn on the instruments for a couple of weeks because they've come up from the Earth and there's always a little bit of atmosphere attached to the outside, and you have to wait for it to outgas. So it wasn't, and I'll never forget this moment either. It was New Year's Eve at the end of 1993, December. I was just cleaning up from a party. The phone rang. It was an old astronomer friend from the Space Telescope Institute. And, Happy New Year, everything. Said, Jeff, do you have any champagne left over from your party? Yeah, we had a little bit in the refrigerator. He said, well, take it out, pour yourself a glass. We just got pictures, first back pictures from Hubble, and it worked. And of course, all of you know the story. This is not a suspense story because the rest has been history, because, Hubble went on to basically all the dreams that people had had for what this great telescope could do were realized many times over. These iconic pictures of the pillars of creation. I mean, it's almost biblical. Let there be light. And then the death of stars, we had the birth of stars, the death of stars in these incredible planetary nebula, which look like, it's like the visions of some surrealistic artists, but this is real. These things are out there in the universe, and Hubble has done such a great job in making all of this available to everybody to look at. And of course, what Hubble has done for cosmology, I'll say a little bit about that in a minute, but I just want to remind you, we were the first of 5 servicing missions. Hubble was designed to be serviced repeatedly, not just because things break. The real value of servicing is as you develop more powerful instruments to put at the focus of the telescope becomes more and more sensitive. So the second mission went up. They actually had some problems too. Some of the insulation was coming out, and we had to figure out how to make new insulation. The third mission went up. This mission was actually cut short. We had a total of 5 servicing missions, but if you notice, it only goes up to 4, because servicing mission 3, do you remember Y2K? Everything was going to come apart when the clock went from 1999 to 2000, and they didn't want the shuttle to be up over New Year's, and so they cut the mission short, and then they put the 3B went out later. And on that mission, they actually removed the beautiful solar arrays that we had put in and replaced them with even better solar arrays. They updated the power system. Just all sorts of new instruments that they put in, and left Hubble in great shape. It was always planned that they would have a 5th servicing mission, because by the mid-2000s, Hubble was getting old. The batteries were near the end of their lifetime. The gyroscopes had failed yet once again. But in 2003, we had the Columbia tragedy. And the administrator at the time, Sean O'Keefe, decided that it would be too dangerous to have any mission other than missions up to the space station. Obviously, if a shuttle went up to the space station and was unable to come home, at least the crew would be safe in the station. But Hubble was off limits, and that meant Hubble was going to die in a couple of years. But we got a new administrator who was a little bit braver, and we solved a lot of the problems. We developed an extension to the robotic arm so that the crew could do a complete inspection of all the tiles. We developed the capability to repair tiles if necessary. We even had a crew trained and a second shuttle ready to go if the primary shuttle needed to be rescued. And they actually worked out a rescue plan where they would bring the people back, and we actually flew that fifth and final mission. And it was incredible because we made Hubble basically as good as new again. We put in new batteries, new instruments, and I'm not going to go through all the details of what was done, but one of the most incredible things was, this is something, you know, every mission we gained more and more confidence of what we were capable of doing as spacesuited astronauts. I mean, on our first mission, yeah, we pulled out instruments and we put in new instruments. By the time of the fifth and final servicing mission, they actually took out instruments, they opened them up, they took out individual electronic boards and replaced them, things which if they had suggested doing that on the first mission, they'd have said, they'd have kicked you out of the room, impossible. But, we really showed what a spacesuited astronaut is capable of doing. And finally, they put in a soft capture mechanism, because someday, Hubble is going to have to be deorbited. We don't want it just to come down anywhere because it's a big telescope. It's not going to all burn up. So the final story is that it really has shown the value of servicing, not just in being able to repair things when they break, but to constantly improve by putting in new and improved instruments. Hubble now has almost 3 orders of magnitude more sensitivity than it was first launched with the original observing instruments. I want to just say a word about the Webb telescope. Some people talk of Webb as a replacement for Hubble. Actually, it's just the opposite. First of all, just to remind you of the incredible size of the Webb telescope. That's a full-scale mock-up at Goddard. And whereas Hubble used the telescope technology of the mid-20th century, where you make the mirror out of one big chunk of glass, astronomers now on the ground had developed the capability of what we call multi-mirror telescopes, and that's what the Webb telescope is. This gives you a sense of the relative observing area. But no, Hubble is, in a sense, even more valuable now, because whereas Webb sees totally in the infrared part of the spectrum, Hubble can see all the way into the ultraviolet. And so taken together, they give us an incredible broad span of spectrum, such that when you look at the picture that Hubble takes on the left, where you see invisible light, a lot of the dust, the infrared light penetrates that dust, and you can actually see the stars being born inside these nebulas. And, it's really amazing when you look at the famous deep sky image that Hubble took, and then the deep sky image that Webb took. You see all these funny shaped galaxies here. Those are the distortions by what we've come to call dark matter. Astronomers have known for a generation or more that just from dynamical observations of galaxies, there is more mass, about 5 times as much mass, in and around galaxies as we can account for in the stars that we can actually see. And we now believe that this so-called dark matter is in Webbs and all over the universe. So when we actually look at these things with Hubble and Webb, we get a much deeper understanding of what's going on. And I just want to sort of finish. I mean, I could talk about the astronomy advances that Hubble has made. You know, many lectures have been given about this. But I'm just going to concentrate on one thing, and that is the Hubble telescope is named after Edwin Hubble. And Hubble, back in the early part of the 20th century, was able to measure the distance to a lot of galaxies, and he also was able to measure the speed at which they're moving towards us or away from us by looking at the red or the blue shift of spectral lines, the Doppler shift. He expected to find as many galaxies moving away as towards us, but what he actually found out was, by and large, most galaxies seem to be moving away from us. And moreover, the farther away from us they are, the faster they're moving. It's as though everything started a long time ago in this, what we've come to call the Big Bang, and the universe has been evolving ever since. And one of the primary goals that was given to two teams of scientists who were given access to the data from Hubble was to find out, I mean, we all knew at this point that the universe is expanding, right? But we also knew that everything in the universe has gravity, so the expansion should gradually be slowing down. But the rate at which it's slowing down was a mystery, and it was very important to determine because it would tell you something about the total amount of mass in the universe. So these two groups individually were told, do the analysis, and then we'll see if your results agree. And they didn't publish anything for like a year or so. What's going on? Well, finally, they got together, and the reason they hadn't published was because both of them had found something. They thought, we must have made a mistake because the acceleration of the universe does not seem to be slowing down. It seems to be accelerating. It's expanding faster and faster. It goes against all known laws of physics if the only force that's around there is gravity. There must be some other force which is pushing things apart, and that became known popularly as dark energy. And it's nice to give it a name because it makes it sound like you know what you're talking about. In fact, we don't have a clue what the dark energy is. We have been able, through use of other telescopes looking at the microwave background, to figure out it's incredible. I mean, almost 3/4 of the universe is, the mass energy content of the universe is this dark energy. And then that dark matter, again, dark matter, we sort of know where it is, although we have no idea what it is. And I'm very sorry to tell you, just like I tell all my students, you know, you've worked hard to learn about physics and chemistry and biology and all that stuff. Everything you've learned about in school only applies to less than 5% of the content of the universe. But you know, isn't that what makes science exciting? And by the way, this is not a Photoshop. That's a real picture of this mysterious question mark galaxy. But as I say, that's what makes science exciting. Every time you answer a question, two new questions pop up. And Hubble and Webb have both contributed to this. And I'll just finish with this beautiful compound picture, which is taken by combining the views from both Hubble and Webb of the spectacular pillars of creation. As far as Hubble, It's, of course, this is a Photoshop picture, but Hubble is still in great shape. As I said, the 2009 servicing mission left it as good as new, and amazingly, it's still going strong, and I hope it will for many years to come. It's been a great adventure for me. I mean, Hubble has certainly rewritten astronomy books many times over, and as an original astronomer before I became an astronaut, what a thrill to have been able to put my own two hands on, one of the greatest telescopes that's ever been built, and actually to bring it back from being almost a useless piece of junk in space to one of the great telescopes of the world. And people ask me, don't I ever get tired of talking about this? I've lost track of how many times I've talked about the Hubble telescope, but it's still a pleasure. Every time I talk about it, it sort of brings back the thrill of being up there and fixing it again. And I always enjoy sharing the experience with an enthusiastic audience like all of you. So it's been a pleasure, and at this point, I'd love to take any questions that you may have. Thanks very much. Oh, good. We got someone brave enough to ask the first question.
So you first.
Yeah, well, I'm not brave enough to get on a shuttle yet, and that's what my question is about. So, how was it getting on the shuttle? This was the second time for you, I think.
No, the fourth time.
Oh, the fourth time. So I guess the first time you got on the shuttle to go to space, how difficult was it? How were you feeling? And then for the fourth time, does it get easier?
People ask me, do you get scared up there? I mean, look, you're sitting on, 4 tons of high, or I don't know how many tons of high explosive. I'll tell you how I approach it. Look, there's a lot of things that can go wrong in a space flight, and obviously we've seen some disasters. Things can happen. What I know is that we train really hard. There's a lot of things, if they go wrong and the crew does the right thing, we can fix the problem. And I was fully confident if anything went wrong that we could do something about. We were well trained, we'd do the right thing, and we could fix it. I'm also perfectly aware there's a lot of things that can go wrong that there's absolutely nothing we can do about. So why worry? But, that's my personality. That's the way I approach things. If sitting on top of a loaded rocket is going to cause you a lot of emotional distress, maybe you ought to think about changing your job. That's all I can say to it. Everybody has to deal with, obviously there's a risk in space flight, and everybody has to deal with that. To be perfectly honest, I think it's a lot more stressful on the families of the astronauts. We're going up on a mission, we're trained, we're excited, we're ready to go and do our work up in space. It's our families who have to worry about, what's going to happen if the rocket blows up, and, what am I going to do, and so on. And, of course, they've seen it happen. My very second space flight would have been the very next flight after the Challenger disaster. So we were very close to that crew. We knew them all, and it's part of the job. But, being an astronaut is not the only dangerous job in the world. I mean, a policeman, a soldier, and a lot of people put their lives at risk. We think it's for something that's worth doing, and that's a decision that I made.
Thank you very much for the amazing talk. I had a question about, so due to the very rapid development for the mission, was there changes concerning a backup crew? Because usually you have backup members in case somebody gets sick, and also were there
We actually did not have a backup crew. when they were getting ready for the second Hubble mission, they assigned me to be their support crew, and if anybody would have gotten sick and couldn't go, then I would have gone on that mission. But we didn't have any backup. We were basically, well, we did it, but that's all I can say.
But did this change any regulations concerning before flight?
Generally, shuttle missions did not have a backup. Back in the Apollo days, every mission did have a backup, and Skylab had backup crews. But we had so many shuttle flights that, you know, there were times when, for various reasons, people had left a crew and someone else got assigned. But by and large, there were no formal backup crews.
Hello. While you were training for your spacewalk, was there anything you encountered during the actual walk that you felt unprepared for?
Well, yeah, when those doors wouldn't close. I mean, remember, that was the very first job on the very first day of our activities. And, you know, I can't tell you what I said under, you know, nobody heard me over the microphone, but when I first went to close that door and the latch wouldn't close, I mean, that was a real shock because, you know, we were living in fear that something bad was going to go wrong, and if we couldn't have closed that door, we would have lost the telescope. So yeah, that was a very big shock. As was, you know, the solar array, but that we sort of were prepared for. We knew what we would do if we couldn't fix one of the solar arrays. And the other problem with the screws, again, that was not something was planned. We just had to deal with it. But that's one of the things, you know, astronauts, we have to be ready to deal with the unexpected. And that's why we do so much training. And they keep throwing problems at us that we have to solve in training, and that gets you used to dealing with the unexpected. So I was prepared for not being prepared for something, if I can put it that way.
Thank you for taking the time to speak to us tonight. My question is about if we're looking forward, looking at James Webb, and then also probably onto habitable worlds.
Well, I hope.
I know. They're stationed at L2, right? So servicing is going to look a little different.
There's no I mean, Webb was not planned to be serviced.
Do you envision any like robotic servicing options in the future?
It really has not even been designed for robotic servicing. Now, it could be that, you know, right now we don't have the capability. It hasn't been designed for it. We did show with Hubble, there's many things that we ended up doing with Hubble that were never planned. I mean, we put in some extra plumbing to allow for a cooling system for a new detector, which had never been originally planned. There were a lot of things that were done, so I don't want to, you know, say that it will never be possible to service the Webb telescope, but it hasn't been planned for servicing, nor has Habitable Worlds or anything else. They're so far away right now, at least for human space flight, we don't even have the capability of going out there, whereas Hubble was specifically planned to be in low Earth orbit so that we could access it with the space shuttle.
First of all, thank you. That was so inspiring to all of us, and it really means a lot that you made the trip here. My question was, with all these spacewalks and missions, I can't imagine that it was super easy on your body. So what did you find the hardest, like physically, to like?
Actually, there have been some spacewalks that have been done which are physically left people very, very tired. Particularly with their hands. But Hubble was so well designed, it was planned to be serviced. I never felt, although, you know, we only went out on every other day, but after every spacewalk, they arranged for us to have a special conversation with the flight surgeons on the ground, and they wanted to ask us, you know, how do you feel? If you had to go out tomorrow, do you think you could do it? And I always felt, yeah, I mean, I feel fine. I could do this, because Hubble really was well designed. It didn't, I mean, there's a certain amount of stress just working in a spacesuit and all the other thing, but it's not like my hands were really, you know, like some people have come back after spacewalks saying that, you know, they couldn't use their thumb for the next 2 weeks. I never had a problem like that.
Yeah, thank you very much for the talk. I was just wondering, of course, you probably weren't, you know, still flying as an astronaut, but you mentioned Columbia. I was wondering kind of what your thoughts were after the Columbia disaster, and if it shook your confidence at all in the reliability of the space shuttle.
Well, I mean, as I say, I was very close to the Challenger. You know, my next flight was a month, would have been, obviously all the flights were canceled. When the shuttle was designed, it was designed with an unbelievable amount of redundancy. There was no crew escape system per se, because the general thought was, well, the shuttle has so much redundancy that you know, you can lose 1 or 2 systems and you can still get back safely. So basically the shuttle itself is your, you know, rescue mechanism. Obviously that didn't account for Challenger or Columbia. Everybody knew, you know, the shuttle it turned out to be rather fragile, and a lot of astronauts paid for that with their lives.
Thank you very much.
Thank you for your talk today. It's an absolute honor and privilege to be able to hear your words about experiencing space and such adventures like so few have had the chance to do. The theme of my question is probably something you've been asked many times before, about the feelings being in space and seeing the Earth from above. I was thinking about how William Shatner went to space recently on the Blue Origin flight, and his quote was widely shared that he felt a feeling of profound grief at going to space for the first time, that he felt it was so empty and so different from how he expected. What did you think about that quote, and did it resonate with your experience?
There's a lot of astronauts who have talked about looking out and how it changes their feeling about planet Earth. And I'll tell you why I think that may be the case, and certainly how it affected me. Yeah, I mean, I'm looking out the window, and I know on the other side of that window is a vacuum, totally hostile to life. And that extends out into the rest of the universe. Almost all of the universe is totally hostile to life. That may be that sense of emptiness that he was talking about. But it goes beyond that, because then you look down at this beautiful blue and green and white and brown planet, our Earth, which, in contrast to most of the rest of the universe, has given birth to life. And it really gives you, I mean, it's like I've fallen in love with Mother Earth again, that sort of a feeling. Some people have come to call this the overview effect. You may have heard that expression. But I think, yeah, it does affect, you know, having been removed and looking at the Earth from this position of, you know, being in such a hostile environment that is totally unsupportive of life, gives you more of an appreciation of, you know, the role that the Earth has played in giving birth to and sustaining life. And of course, that leads to our need to protect the Earth and all the other things that go along with it.
Thank you.
Thank you so much, Professor. So you spoke about the pressures from the Congress and public about the Hubble disaster. Could you talk a little bit more about how you grappled with that pressure and that responsibility, and maybe some advice you have for the future explorers?
Well, you know, in a sense, I've had 5 space flights, and every single flight, and this is true about every crew that goes up, no matter what the mission is, they want to do it perfectly, and that's the way we felt. I mean, we knew externally Hubble was something special. You know, I talked about Congress. I was telling this to somebody on the way over, but when we were training at Goddard one day, we got a message that Dan Golden, who was the head of NASA at the time, wanted to meet with us. So we went to NASA headquarters, and we went to his office, and basically all he wanted to say to us was, well, people, I hope you realize that the future of NASA's human space program depends on the success of your mission. So, like, you know, no pressure. Sure, there's a lot of pressure. Externally, Hubble had a lot more of that. And NASA did their best to keep us insulated. I mean, they had probably, I think, 13 or 14, every month there was a new committee formed to study, you know, are we really doing the right thing? Is there anything else that could be done? And the first thing they wanted to do was to talk with the crew. And that ended up taking a lot of time. And so finally, NASA appointed a mission manager, and they said, you can't talk to the crew. Anybody who wants to talk, you talk to the mission manager and let the crew get on with their training. So yeah, we recognize the importance of it, but every single mission that every astronaut goes on, they want to do 100% perfect, and we looked at it the same way. But yeah, I mean, for sure, we knew that objectively, it was critically important, and you just deal with it.
Thank you.
Thank you, Professor, for the fascinating lecture. And this question comes from my curiosity. So how was the crew for EVA was selected?
Well, as I say, they wanted people who had previously done spacewalks to make sure that, you know, we knew what we were doing. You know, why particularly I was selected? I mean, there were a lot of people who had done spacewalks. I will say, you know, I explained on my first flight where they sent me out, you know, to do an unplanned spacewalk, so that was pretty special. And people told me when I got back in, hey, Jeff, you look good in a suit, you know. So I think all of us, you know, when you come back from a mission, you get rated. You know, your commander writes a report on you. The people who have trained you, they write up, you know, how well did they do and so on. And I guess all of us had gotten good marks on our spacewalks that we had previously done, and so that's, I guess, why we got selected. I was not in on the selection process, so you know, there may have been other things that went on, but all I know is that one day I got called to the head of the astronaut office, and he said, you know, Jeff, I think I should let you know they're getting ready to choose the crew for Hubble, and you're on the short list. And so, you know, I had kind of dreamed about, oh, wouldn't this be great? But, you know, so many people wanted to be on the flight. But when I heard I was on the short list, and then about 2 hours later, I got another call saying, well, congratulations, you're on the mission. That's how it looked like from my point of view. And at that point, I didn't really care how they made the selection. I was just glad that I got selected.
Hi, thank you for your amazing talk and what I only can imagine to be an amazing adventure. With our technological advancements from today and the amount of rockets we launch, do you think there should be more Hubble telescopes in the sky to look for everything in the universe?
Well, I mean, there are more telescopes being planned. You just heard about the Habitable World Observatory, and yeah, I mean, we're not going to build. Well, let's see, and then also we have some other mirrors the size of Hubble, and that's we'd like to launch a telescope with one of them. Whether or not that's going to happen in the current budget environment, I don't know. Yeah, I mean, there's always more things you can do. Although, remember, it takes a lot of people to operate a space telescope, and people cost money, and there's a limit to how many people we have operating them. So, it's not just a question of building the telescopes and launching them. You've got to operate them, and you've got to have enough money to pay scientists to analyze the data. If you don't have the resources to support the telescopes, then there's no point launching them, because you're not going to be able to do anything with them. And that's a real problem these days.
Hi, thank you so much for such a fantastic lecture. This is another question out of curiosity. So if you're traveling on an aircraft or a ship, you get seasick, airsick, and nothing can really be done until you actually end the journey and remove yourself.
Well, there's pretty good medications these days.
Yeah, that's true.
And by the way, there is no correlation that's ever been determined between people who get seasick, airsick, and people who get space sick. So it's kind of the luck of the draw. But as I say, we have good medications for it.
So in a spacecraft, during any of your time traveling, whether it's outside or within the shuttle, have you ever felt anything, and is there anything you can do?
No, fortunately, I never had I don't have a particularly strong stomach for doing acrobatics in airplanes, but I never had a problem with space sickness. I've seen people who have, they can fly acrobatics all day, but they get sick in space, but other people don't. There doesn't seem to be any correlation. It's not a real problem. Like I say, we have good medications for it, and particularly nowadays when we're going up for 6 months on the space station, if you're not feeling quite up to par the first few days, no big deal. It was a much bigger deal in the early days of the shuttle when we had short missions, and if you have a 5-day missions and you're feeling sick for the first 3 days, that's pretty serious.
Okay, and may I also just quickly ask, thank you for sharing the photos of the underwater training that you had for the walks. How relevant, how identical is it to the actual spacewalk? Does it match quite closely?
It's remarkably similar. As I say, you have to appreciate that the water has a viscosity. And that may be also one reason why they wanted people who had done spacewalks before, because we knew the difference between training underwater and working in space. But I'll tell you the experience I had on my first space flight when I did that unplanned spacewalk. I always remember I opened the hatch and I was facing down towards the floor of the shuttle, and I had to sort of translate over to the tool chest to get the tools to put on my tools. And I remember thinking, as I was putting all the tools on, thinking, wow, this is really like being underwater. I really feel well trained for this, and it's a good feeling when you're out doing something critical, and you feel, oh yeah, I've done this before the training. And then I turned around, and there was the Earth and the sky, and I said, oh my God, we're not in the water tank anymore. And that's when it really hit me.
First of all, I would like to say thank you for an amazing presentation. It was totally inspiring and amazing. And also, if it's appropriate, I would like to say thank you for your service.
I can honestly say it was a pleasure.
Thank you. So, the question. I'm just curious. Are you currently retired, or do you still work in the space sector? And also the second question.
Wait, am I still what?
Retired.
A what? No, I'm a professor at MIT.
Okay. But the only professor, nothing else.
Only a professor?
Yeah,
sure.
Okay.
Yeah, okay.
And also the second question: if someone offered you the opportunity to go to space again, would you say yes?
Oh, in a moment. Just don't tell my wife, please. She would not be happy.
Okay, thank you.
Thank you, Jeff. Thank you for such a wonderful talk. You are one humble guy, just selected and just a professor. So I just want to remind everybody that this was the first of our distinguished lecture of a series of them open to the public. And I have about 100 more questions. But next Wednesday at the same time here, we will actually have an astronaut panel with 3 astronauts. Jeff, Robert Thirsk, a Canadian astronaut, as well as our very own here in Korea, Soyeon Yi. So that will be a great one for all your other questions. Tonight.
And I will say, I've been trying at lunch to sit down with and meet as many of you students as possible, because, that's one reason I like coming to ISU, is to get to meet all of you. Every year it's a different student body, so, don't be shy. I'm happy to talk, and I love talking about space, so we'll have those conversations. And I'm here for another week.
Great, great. It's also about a 20-minute walk, so you can walk with him each way. So for now, we're actually going to end the night. There is a reception downstairs in the lobby, and we can be here until about 9:50. So feel free to ask more questions.